Hi everyone, so today we're going to talk about weight and weightlessness and what that means. So if you remember back when we talked about forces, we talked about weight, and we said that weight is defined as the magnitude of the force due to gravity. So you probably remember this formula here, that your force due to gravity is equal to m times g, where g is the acceleration due to gravity and m is the mass, right? And that's our weight of whatever object we're looking at. So in order for an object to be actually weightless, that means that it has no weight, right? If you look at this formula, the only way for this to happen is to have either a mass be equal to 0, which is not possible because we don't have the object, right? We have to have mass in order to be an object, or our acceleration due to gravity has to be 0. This pretty much doesn't actually ever happen, right? Because there's always gravity acting on you, even if it's very, very, very small, right? So the closest we can get to this is out in deep space, where we're far away from planets and stars, right? Even though we're far away, we still technically have a tiny bit of gravitational pull, and there's a tiny bit of weight, but that's as good as we can do. But we also have the phenomena called apparent weightlessness. Before we get into the details of what apparent weightlessness is, let's talk about what a bathroom scale does. We should note that bathroom scales, they don't actually measure your weight. They measure the normal force that they're producing. So if we have a bathroom scale, say on your bathroom floor, and the scale is not accelerating, right? So we have something that's not accelerating, we know that the force is balanced, right? So we have gravity acting down on the scale and the normal force of the scale acting up on you, right? So in this case, the force is balanced, so we know they're going to be equal. So the normal force that it reads is going to be equal in magnitude to the value of your weight, right? So when the scale is not accelerating, we get your correct or accurate weight value. I'm going to be talking about this in terms of an elevator. So here we have a person in red on a scale in an elevator. The elevator is at rest. Our force is balanced, so the scale reads your weight value. Now, when we have if the elevator is moving up or down, or I should specify is accelerating up or down, the forces are no longer balanced, right? Remember, if we have an acceleration, that means we have a net force. Remember Newton's second law, F equals ma. Our net force is equal to mass times our acceleration. So if we're accelerating, that means we have unbalanced forces, right? So if our elevator is accelerating upwards, that means that our up forces are going to be larger in magnitude than our downward forces. So our normal force is larger than our gravitational force in this case, and that means that our scale is going to read a larger weight value. So we're going to have a larger apparent weight, right? Now when it comes to the elevator accelerating downwards, that means our net force is going to be in the down direction. So our normal force is going to be smaller than the gravitational force. So we're going to have a smaller apparent weight. We're going to appear to weigh less than we actually do. Right? We can see these in these pictures down here at the bottom. The picture to the left shows a person in red on a scale in an elevator. The elevator is not moving, so they have an actual weight of 700 newtons. The second elevator here is an upward acceleration, so we have larger apparent weight. The third elevator, we have an acceleration downwards, so that has a smaller apparent weight. And then finally here, we have an elevator where, as horrible as it sounds, the cable snaps, so the elevator is in free fall. He looks very calm for this situation, but since the elevator is in free fall, we actually have no normal force anymore, right? So we have free fall. It's not going to read any normal force. This is what's known as weightlessness, right? So in free fall, we have apparent weightlessness. Now, just a reminder, any object that is in free fall, any object that's in orbit an orbit is, man, my words are all jumbled. So remember that an object in orbit is in free fall, right? So if it's an object orbiting another object, it has apparent weightlessness, right? So the International Space Station is in orbit around the Earth. So the apparent weight of the space station is 0. It has no weight, right? And this is the case for here. I show an image of someone skydiving. Skydiving, they're in free fall. If we ignore air resistance, they're in free fall. They have no apparent weight. Same thing here with someone out in space. They have apparent weightlessness. And finally, I leave you with an XKCD comic. If you're not familiar with their comic, they're pretty funny if you're a science nerd, specifically a physics nerd. But here's one they did about weightlessness, right? And I hope you enjoy. Right, bye everyone.